Welcome to all of you. Now we discuss paper CC-10 units 1 and 2 2022 mechanics semester 4 mathematics honors. Question paper 2022 units 1. Question 2a. A ladder whose center of gravity divides it into two portions of lengths A and B rests with one end on a horizontal floor and the other end against a rough vertical wall, so that the inclination of the ladder to the floor when it is in limiting equilibrium is tan inverse this, where mu and mu dash are the coefficients of friction of the floor and the wall respectively. No figure, no marks. So we must draw the figure, and this is the floor horizontal, this is the vertical wall OB, ladder is AB. AB is be the position of a ladder of length A plus B, and G be the center of gravity of AB such that AG is to GB equal to A is to B. Let R and S, this is the R and this S, be the normal reactions of A and B at the point A and at the point B respectively, and W be the weight of the ladder, so it acts vertically downward from G, resolving all the forces horizontally and vertically. We respectively get this S, so this mu r in this direction, so S equal to mu r, and this vertical upward vertical direction R, and this mu dash S, so downward direction W, so R plus mu dash S equal to W, where mu and mu dash are the coefficient of friction of the floor. Mu is the coefficient of the friction of the floor, and mu dash is the coefficient of the friction of the wall. From 2, R equal to W minus mu S dash, so uh, S equal to mu R, so W minus mu dash mu R. So R equal to W by 1 plus mu into mu dash, equation 3. And S equal to mu into R, value of R from 3, W by whole divided by 1 plus mu into mu dash. Let theta be the inclination of the ladder to the floor. This is the theta, is the inclination of the ladder to the floor, this theta angle. Then taking moments or forces about A, about A, and these forces are passing through the point A, so there is no moment for the force R, and this mu R also passing through the point A, so there is no moment for the force mu R, and we have only this force W, and for this force S, and for this force mu dash S above the point A. Now this W into A cos theta, so this W force, and this distance is A, GAA, and from the right angle triangle we get this force W, and the perpendicular distance from the point is equal to A cos theta, and this is the in anticlockwise direction about the point A, so this moment is positive. So for this force W about the moment about the point A equal to W into A cos theta, and for the force S, this force S, so distance, perpendicular distance from the point A is this BO. So this right angle triangle A, B, and O, this theta angle, right angle is this. So this distance is hypotenuse is A plus B. So this height actually OB equal to A plus B into sine theta. This A plus B into sine theta. And this force S force, the moment of this force is clockwise direction about the point A. So this clockwise direction about the point A. So this negative moment. So we get this minus s bracket a plus b into sin theta. And for this force, mu dash is about the point A. This mu dash is, this force mu dash is, uh, so distance from, perpendicular distance from the point A, this OA. So this OA from the right angle triangle ABO, we get this equal to A plus B into cos theta. And this force, this moment is clockwise direction. So this is minus mu dash is A plus B into cos theta. Simplifying this value of s, putting by from 4, this 4 mu w by 1 plus mu dash. So we get this is equal to dividing by cos theta. So this equal tan theta equal to this, and after simplification we get tan theta equal to this and theta equal to tan inverse this. Proved. Next question 2b. Forces capital X, capital Y, capital Z act along the three lines given by the equations y equal to 0, z equal to 1, z equal to 0, x equal to 1, x equal to 0, y equal to 1. Prove that the pitch of the equivalent range equal to this. So no figure, no marks. So we must draw this figure. Now x vector, capital X vector, acts along the this y equal to 0 and z equal to 1, this line y equal to 0 and z equal to 1, this line, this axis is x-axis, this y-axis, this z-axis, this point O as origin, definite origin, and this point C with coordinates 0, 0, 1, and this line is parallel to the x-axis, and at this point C, and force this x vector acts along this line, y equal to 0, z equal to 1, and symmetrical form is equal to x minus 0 by 1, y equal to y minus 0 by 0 equal to z minus 1 by 0. And capital Y force acts along the line z equal to 0, x equal to 1. So this equal to x equal to 0, y equal to 1, y force, sorry, this at this point A with coordinates 1, 0, 0. This point A parallel to the y-axis, this force acts along the y-axis parallel to the y-axis. So symmetrical form of this equation of this equation, line of this equation is x minus 1 by 0 equal to y minus 0 by 1 equal to z minus 0 by 0. And z force, vector z, acts along this line parallel to z-axis at the point B with coordinates 0, 1, 0. So this symmetrical form equation of this line x minus 0 by 0, y minus 1 by 0, z minus 0 by 1. And the scheme for the forces x and y and z are respectively, actually this upper row is the point where the force applied is applied, and this second row for the component of the forces. So x vector equal to component x I cap plus 0 j cap plus 0 k cap. So these components of this force x 0, 0, and the point of application of the force x is this 0, 0, 1. So this scheme is this 0, 0, 1, and for this force y is 1, 0, 0, 0, y 0, 0, 1, 0, 0, 0, z. And r vector with the resultant of the force of the system, then r vector equal to this x dash, y dash, z dash, this component parallel to the x-axis, x-axis, y-axis, z-axis, and this. So x dash equals to x plus 0 plus 0, and this x along the x-axis, so this x plus 0 plus 0, and y dash equal to 0 plus y plus 0. So actually x dash equal to x, y dash equal to y, z dash equal to z. And if L, M, N, capital M, N, be the components of the moment of the resultant couple G of the system about the axis, so L equal to L1 plus L2 plus L3. And this actually L1, M1, N1 be the components of the moments of the couple above of the force x vector about the axis, So L1 is the for the force x force about the x-axis. M1 is the moment about the y-axis. N1 is the moment of the force x about the z-axis. And similarly for L2 empty N2 and L3 M3 N3. So L1 equal to 0 0 Z. The moment of x vector about the axis x is 0. So this equal to 0. So L equal to this, Z, M equal to x, M equal to y. And the pitch P of the range P equal to gamma by R. The formula is Lx dash plus My dash plus Mz dash whole divided by root over whole divided by x dash square plus y dash square plus z dash square. So x dash equals to x, y dash equal to y, z dash equal to z from 4. Put all these values, we get P is equal to this proof. Now, the extra portion is the equation of the central axis. The equation of the central axis is this formula is this L minus small y capital Z dash plus small z capital Y dash. Actually, small y small z is the coordinates, and capital X capital Y are the component of the forces. And this formula, and after simplifying, putting using the values of x dash y dash z dash from 4 and 5 and element in, and we get the equation of the central axis is this. Next question, unit 2. Unit 2, this question 3a, 6 equal rods, 6 equal rods. Actually, this question is coplanar forces, gravity this, and this question B coming from forces in 3D, and question 3a actually virtual work, and question 3b the stability from statics portion. Question 3a, 6 equal rods each of weights W are freely jointed at their ends to form a regular hexagon. The rod AB is fixed in a horizontal position and the middle points of AB and D are jointed by a string. Prove that this tension is 3W. No figure, no marks. So you must draw this figure. This is the regular hexagon A, B, C, D, E, F, and formed by the 6 rods of weight W, and the length of each rod is twice A, and let the rod A be placed on the horizontal plane XY. In the position of equilibrium, this angle CBY equal to theta, and T with the tension. This tension of the string MN. N is the midpoint of ED, N is the midpoint of AB. So this tension string, actually tension arrow is the inward direction, and this W for this each rod from acts vertically downwards from the center of gravity of each rod. This portion middle point, from the middle point this W vertically downwards, this W, this W, this W, this W. The total weights is 6W for 6 rods. Acts their CG. So the system, this G is the total resultant CG of this system. So this 6W actually acts vertically downwards. This 6W from the point G. And the midpoint of Mn, actually this midpoint of Mn, this G is the midpoint of Mn, M and N, and the height of the G above the this plane, horizontal line XY, this height is actually Gn. This is equal to twice A sin theta, because this length is CB is the twice A, and this angle is theta. So from this right angle triangle, this we get this height is twice a sin theta. This twice a sin theta. So this height is parallel to this height. So actually the height is twice a sin theta. And similarly, from MG is also twice a sin theta. And so total distance from MN is equal to 4a sin theta. Let the system be giving a small symmetrical virtual displacement in which theta changes to theta plus delta theta. Then the equation of virtual work is equal to 6W delta twice sin theta is the distance, as this 6W is the weight vertically downwards from the point G, and this baseline is this XY. So above the baseline, virtual work is negative. So below the baseline, virtual arc is positive. So convention by convention, this virtual arc from for this force 6W, the height is twice a sin theta, so it's minus 6W because this force above the baseline, so this minus 6W delta twice a sin theta. And this tension, so tension acts this inward direction, and conventionally this tension is negative. So T minus T delta, and this string distance of this length of the string is equal to Mn, actually this is equal to 4 sin theta. So this twice a constant, so this equal to twice a, so 6 into 12a, and cos theta delta theta, and this equal to uh, uh, 4a into cos theta delta theta. Actually, negative sign common, so we get plus and plus both. So we get this delta theta not equal to 0. A small variation, virtual work, very small. This 4a cos theta 3w plus t equal to 0. Also, this theta is not equal to 0, 4a cos theta not equal to 0, because theta equal to cos theta equal to 0, theta is 90 degree. So 3w equal to t. Actually, t equal to minus 3w. Here, negative sign shows that this T is not a tension actually. The real field, this is actually thrust. Actually, this is not a string. Actually, this is the rod. So thrust, actually thrust. If there is a rod, amen, and thrust, and then this force T, the outer direction. This outer direction. So actually, this is not a string. Actually, this is the thrust. This thrust, and hence the thrust is 3W. Question 3b. A body consisting of a cone and a hemisphere on the base rests on a rough plane table, the hemisphere being in contact with the table, so that the stability for the equilibrium, the greatest height of the cone is root 3 by 2 times the diameter of the hemisphere. No figure, no marks. So this is the hemisphere, and this upper portion is the cone. So, and this is the plane on which this hemisphere touch at this point A. Let capital H and small a be the height and radius of the base of the cone. So this is the height H, and this is the base with the radius small a, and G1 is the center of gravity of the cone. So OG1 equal to H by 4. This is the length of this center of gravity of the cone. And next, G2 be the center of gravity of the hemisphere is G2. So OG2 equal to 3a by 8 from the chapter center of gravity. So we get this. Remember this result is 3a by 8 if base is a. Clearly, AG1 AG1 equal to AO plus OG1. OA is the radius A plus H by 4, and AG2 equal to OA minus OG2. AO is the A, and OG2 is the 3A by 8. So this is the 5A by 8, AG2. Actually, the height of the center of gravity of the cone G1 from the base point A, and this is the center of gravity of the hemisphere height of the center of gravity from the base point A, this AG2, where A is the fixed point of the contact between the hemisphere and the horizontal plane. And let W1, W2 be the weights of the cone and the hemisphere respectively. And then this W1 by W2 equal to volume of the cone by volume of the hemisphere. So this volume equal to 1 by 3 pi square into h height formula, the volume of the cone, and the hemisphere. So this half 4 by 3 pi into a cube. This is equal to h by twice a. So W1 by h equal to W2 by twice a equal to some constant c, non-zero constant c, say. Then W1 equal to ch, W2 equal to twice ca. Let G be the combined center of gravity of the body, and of the body means this hemisphere and cone, and this is the G is the combined CG. So this height of this H of this combined center of gravity from the base point A. So this AG equal to small h, AG equal to small h, and the formula for this small h equal to AG1, the actually this is the height of the center of gravity of the cone into the weight of the cone plus height of the center of gravity of the hemisphere into the weight of the hemisphere, the whole divided by sum of their weights, W1 plus W2. So put all these values from the previous result, and after simplification, we get this. Now at the point of contact A, this is the point where contact A, hemisphere and plane, point of contact A, and this is the smaller is the radius of the curvature of the hemisphere is equal to A. Actually, radius is the radius of curvature here. This is the radius for the hemisphere, and capital R is the radius of curvature of the plane. So this equals to infinity. So for stability, for stable equilibrium, we have 1 by E is greater than 1 by small r plus 1 by capital R. And this is, remember this result. This 1 by h, actually small h equal to this. So 1 by h equal to this 4 into capital H plus twice a whole divided by 5 a square capital H square plus 4h greater than 1 by a, 1 by r is the infinity, so 1 by r is 0. And after simplification, we get h is less than root 3a. Actually, we divide 2 and 2 by 2, then twice is the diameter. So in the given question, is the root 3 by 2 times root 3 by 2 times the diameter of the hemisphere. So we write here h is less than root 3 by 2 into 2a. 2 is the diameter of the hemisphere, hence the result. Thank you for watching this video, and this PDF of this solution is given in the description box.